Alright, in this podcast we're going to talk about metallic bonding. So we can think about metallic bonding like this picture. So imagine you have a sheet of iron or copper or gold or anything, and you have all these atoms that are pretty nice and neatly arranged. What you have is their valence electrons don't stay locked in place with the individual atom. Okay, they are able to move in what's known as a sea of electrons. Okay, so let's take a look at what that looks like, this sea of electrons. So for instance, here I have a metal, and I have this atom right here where there's a pretty high concentration of electrons, and this area here where there's a low concentration of electrons. So what's happening is electrons are able to move, this is valence electrons, are able to move away from the nucleus or the core of its atom to neighboring atoms. And we call this a sea of delocalized electrons. Delocalized means that they're local to their own atom. Delocalized means that they're able to move. Okay, so what's an alloy? An alloy is a mixture of two or more metals. And as you can imagine, if they are going to be mixed, that you have to heat them up to really, really high temperatures. So for instance, brass is an alloy of more than one metal, and steel is a big industry that involves making alloys, and you've probably seen on TV the really, really hot containers where they melt them and mix them. It's not a chemical reaction, it's just a physical change. It just requires a whole lot of energy to get them melted so that they can mix. Some common properties of metals are that they're malleable, ductile, and they conduct both heat and electricity. So let's take a look at how the structure, this sea of electrons, leads to the properties that metals have. So the first thing is, from an electrical conductivity standpoint, for the most part, if I have an atom, it's going to, or if I have a sheet or a piece of wire, the valence electrons are going to be near their nuclei. But if I were to put let's say a positive end of a magnet close to that metal, the electrons that were on this side are going to shift towards that positive charge, and there's going to be a high density of electrons near the positive. Just like if I were to put a negative side of a magnet here, it's going to push the electrons away. Okay, so this movement of the electrons through this is what makes it electrically conductive. Okay, if I apply heat, these atoms can vibrate, and they can, because there's this movement of electrons in between, it can easily conduct the heat, bouncing from one atom to another, passing that heat along. Okay. This shows what happens if I deform the metal. If I just push on it, let's say with a hammer or something, I can push these atoms in this sheet and cause a different shape. And that's the malleability. So if we look at that, we'll look at that in 1 second, but let's first take a look at this interesting chart where we see some melting points of different alkali metals and alkaline earth metals. So if you look at the periodic table, these are group 1 and group 2. The group 1s have, what they show is lithium with one valence electron has a melting point about 180 degrees, but beryllium has a melting point of 1200 degrees, more than 1200 degrees. And you can see that in all cases that within a period, the one valence electron has a relatively low melting point compared to its element beside it that's in the group 2 with two valence electrons. So the fact that there's two valence electrons contributing to that sea of electrons makes those metallic bonds even stronger, raising the melting point. So what's causing the increase in melting point here is the 2 valence electrons versus the 1 valence electrons here. Now as you go down the group, you also see in general a reduction in the melting point, and that's because the smaller my atom is, the closer the nucleus of that atom is going to be that's available to be attracted to that sea of electrons. So the bond is going to be stronger. So lithium is going to have a higher melting point. It's going to take more energy to disrupt that network associated with the sea of electrons. And here's where we're looking at the malleability. If I were to take a hammer and I push on a piece of metal, it's going to cause these atoms to shift, okay? But it's not like when we saw this with the ionic compounds, where the shifting would cause positive and positive and negative to line up, causing this shattering, that the brittle properties. The metal just moves, it just deforms, because the electrons just move with it, causing this to be malleable. Okay, so we're going to stop right there.